Okay, so last time we talked about the entanglement structure in quantum mechanics, and the well, the key idea that I discussed was that the key fact was that the ground states of local Hamiltonians have low entanglement. They have area law entanglement, and this is also going to be true in quantum field theory. The last thing I wanted to say before we go to quantum field theory, however, was that this area law is the basis for a technique called matrix product states. And oh, I got a new marker and it's still not working.
I don't know if the recorded video can see the words.
Because it's too light? Yeah. Let's try purple. That'll work. It's going to work for about 30 seconds and then, okay, let's try it. Is it working now?
That's better. The purple's better.
Yeah.
Okay. So matrix, that says matrix product states. So the idea is that there's a very simple ansatz that can capture that you can use to write any wave function with area law entanglement. Okay, and we said that that's very special because the ground states of local Hamiltonians have area law entanglement. So here's the ansatz. The statement is that any 1D state with the entanglement of a region A bounded by 2S naught as the separation between, well, I guess I meant the length of A. Goes to infinity. Can be written in the matrix product form. So the matrix product form is the following. So we sum over all the spins. Now, last time I wrote an equation that was just a totally general wave function on n spins, and it was just a tensor with n indices on it, one for each spin. But now the matrix product form is a product of matrices. Okay, so it's M, I1, I2, sigma 1, M, I2, I3, sigma 2, etc., up to M, I, whatever I that is, I1, sigma n, sigma 1, dot, 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 sigma n. I'm using periodic boundary conditions, which is why the matrices are multiplying this way. So we're just multiplying a bunch of matrices together. And there's the indices here, there's a physical index. There's a physical index which corresponds to the Hilbert space of the spins, one for each spin. And then there's this auxiliary index, which is just an auxiliary thing that we introduced. And the rest, sorry, I didn't finish writing the statement here. So where these bonds, the IK, which are called the bonds, have run from 1 to big D, where big D is e to the S naught. Sorry, S naught. Wait. e to the s naught. Yeah. Okay, so what's the advantage of this? The advantage is that we went from having 2 to the n complex numbers in a totally general wave function to having, in this case, now each of these matrices has n from there and then d squared from there. So this has become n d squared. And now the important point is that when you take the system size to be very large, well, if it's translation invariant, you don't even need this n because all the matrices are the same. So then when you take the system size large, your ansatz does not go with the system size. Now, and people like to draw pictures of these things. So the picture for this matrix product state is just like this. So each of these dots is one of these matrices, tensor. The hanging indices are the physical indices that correspond to the spins, the sigma indices. And the contracted lines are the matrix multiplications. Okay. So an ansatz like this is not going to capture typical states. As we talked about, typical states have volume law entanglement. So the bigger the region, the more entanglement. But when you have these matrix product type states, basically these bonds are encoding the entanglement. And the more entanglement you have, the bigger you need the bond dimension d. But if you have finite amount of, if you have area law entanglement, like in ground states, then you can encode that very efficiently because it's not growing with the system size. Okay, so you can think of this as sort of you can think of it either as like a data compression, that you can take what was a whole lot of numbers and encode them in a smaller number of numbers, but more physically speaking, this is renormalization. This is the renormalization group in action, and there's a whole lot of work on understanding spin chains this way and renormalization techniques based on this ansatz. Yeah.
So we went from a statement about the ground state to a statement about any 1D state?
Well, sorry, this statement is just a statement about, this statement is just true, that any state can be represented this way, basically as long as the bond dimension is big enough to encode the entanglement. Now, it also happens to be true that ground states of gapped local Hamiltonians satisfy this assumption. So in particular, the ground state of a gapped Hamiltonian can be written in this way. If it's not gapped, then you have logarithmic corrections, which means that you have to increase your bond dimension a little bit with the system size, but you're still going to do much better than you would just writing down a totally general wave function. This underlies a method called the density matrix renormalization group. Basically, quantum mechanics in one space dimension like this is numerically a completely solved problem. You just give me any Hamiltonian, you can use this to find its ground state and solve it. Well, you might like to know about excited states too, and you can't necessarily get at the excited states with this. But as far as finding ground states, it's solved. Okay, now we're going to turn from quantum mechanics to quantum field theory. So subregion entropy in QFT. So we're in some state rho, and space looks like this. And there's some region A in space. As I discussed at some point briefly earlier in this course, it's almost true, and it's pretty close to being true, that the Hilbert space of quantum field theories factorizes into a factor associated to the inside of region A and a factor associated to the outside of region A. The entanglement entropy of rho A is UV divergent. There's various ways to think about this. One way to think about it is that quantum field theory has lots of short distance stuff, and it goes to very small scales, so you get UV divergences from the entanglement of this stuff across the cutoff. Maybe another way to think about it is going to our quantum mechanics example. We said that quantum mechanics has area law entanglement, but area has units. Okay, so area in units of what? And the answer is the lattice spacing. Okay, so if you start with quantum mechanics with area in units of the lattice spacing, and then you try to take the continuum limit, go to quantum field theory, then that lattice spacing is going to show up as a UV cutoff. So the structure of the entanglement entropy in quantum field theory generally looks something like this. It's something over epsilon, so this is d space-time dimensions. So the leading term is an area law divergence. Epsilon here is the UV cutoff. So you should think of taking epsilon to 0. In quantum mechanics, you could calculate this, and it was meaningful, and it was the leading term in the entanglement entropy. In quantum field theory, it is physically meaningful. Like, there really is an infinite amount of entanglement in quantum field theory. It really is there, but you can't calculate it. Its coefficient doesn't mean anything because it's scheme dependent. It depends on exactly how you do your cutoff procedure and everything. Okay, so it's really there, but you can't calculate it, or at least you can't calculate it in any meaningful way. Then there are subleading UV divergences, depending on how many dimensions we're in. So like if we're in 4 dimensions, this is 1 over epsilon squared, and the next divergence is logarithmic. So there's a number times log epsilon. The logs only show up in even d. And then there are finite terms. The coefficients of this, the coefficients of the divergent terms have to come from UV physics. Like, nothing about the infrared can influence the divergent terms. Because any kind of long distance stuff is not going to contribute to the infinite part. The infinite part is completely about the physics infinitesimally close to the dividing surface. So these coefficients can only depend on the shape of the cutoff surface. They can only depend on the shape of this surface. So it's an integral over dA of some geometric invariance, like the extrinsic curvature of A and stuff like that. So we have to be very careful when we talk about, so any kind of entanglement calculations that we do in quantum field theory, and when we go to apply all these inequalities that we talked about last time, we have to be very careful with these UV divergences. Okay, we can't just because it's infinite doesn't mean it's zero, and it matters. Okay, so let me give you an example just to sort of as a quick little warm up of how we deal with these divergences. Let's say we're doing a situation in quantum field theory where you have three regions, A, B, and C. Subadditivity, say for regions A and B, says that the mutual information I of AB is non-negative. Remember, the mutual information is S of A plus S of B minus S of AB. This is non-negative. And we might like to learn something about quantum field theory from an inequality like this, but it's totally trivial. Subadditivity is in this setup is completely trivial because it's already true from the UV divergences. So the UV divergences, the leading divergences in this expression will be the area law terms. So the leading UV divergence here is going to be the area of A plus the area of B minus the area of AB. But this piece is not going to get subtracted off when we calculate that difference. Okay, so if all these things have length 1, then this is 4 times infinity plus 4 times infinity minus 6 times infinity, which is indeed positive, but it's not very interesting. When things get interesting is when you can cancel off the divergences and still have something left over that's not trivial. So to give you an example of that, let's look at strong subadditivity for that same configuration of A, B, and C. So strong subadditivity, recall, says SB plus SABC is greater than equal, less than equal?
Yeah.
Less than equal. My notes got it backwards. Less than equal SAB plus SBC. So if you look at the area law divergences here, you can add them all up and they cancel on the two sides. So like this one has 4 infinity, this one has 8 infinity, this one has 6, and this one has 6. Okay, so for every piece of that boundary that shows up on the left-hand side of this inequality, that piece of the boundary also shows up on the right-hand side of this inequality. So all the divergences cancel off. So strong subadditivity in this situation actually says something interesting about quantum fields. Okay, and that's the kind of thing. That's the kind of trick we have to do when we use entanglement to study quantum fields. This is just some simple example, but that's what we have to think about is ways of canceling the divergences and being left with something meaningful. I'm going to write a couple examples of entanglement entropies in quantum field theory, and we're going to come back and calculate them in like 2 lectures or so. But I just want to write the answers now so that we can stare at them and kind of see what entanglements look like in an example. So in 2D CFT, we're going to do this calculation later, but here's the answer. So space is just a, let's say space is the real line. So region A, if we pick a region, region A is just an interval on the real line. You know, entanglement is about regions in space, not in space-time. So let's say region A has length L. In the vacuum state, the entanglement entropy of region A has a famous formula. It's C over 3 log L over epsilon, where epsilon here is the, L is the size of region A, and epsilon is the UV cutoff. Now, the fact that there's a UV cutoff here means that if you add a constant term to this, like, I don't know, add 5 to this or something, that can be absorbed into the cutoff. Okay, so there's a constant shift, which is non-universal, but the coefficient of the log term is universal and is given by the central charge of the CFT. We're going to do this calculation next week. This is sort of an area divergence. Of course, area in one dimension would be L to the 0, but it's area divergence with a log correction. So it's almost area law. In a thermal state, you can again do this calculation, and S of A in a thermal state is C over 3 log beta over pi epsilon sinh pi L over beta. Okay, so this has a little more structure to it. So let's look at different limits. If L is much less than beta, the inverse temperature, then you basically don't notice that you're in a thermal state. If you're in a thermal state and you go to distances much less than beta, then you don't notice the thermal state. You're basically in vacuum at short distances. And indeed, in that limit, the sinh just becomes pi L over beta, and so if L is much less than beta, we get back C over 3 log L over epsilon. So this is reflecting the fact that short distance entanglement in quantum field theory is always set by the vacuum state. Everything is vacuum at short distances. If we look at L much bigger than beta, well, then we can approximate this sinh by an exponential. So we have log of an exponential, so it's linear. Okay, so if you plug in L much bigger than beta, this gives you C over 3 times pi L over beta. Plus dot dot dot, where dot 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 includes an infinite term. So, but this term is meaningful. Okay, so this term scales with volume. And you can think of these terms like this one that scale with volume, extensive terms, you can separate that from dependence on the UV cutoff. So this is a physically meaningful term. And it has a very natural interpretation. This is actually equal to the volume of region A times the thermal entropy density, the thermodynamic entropy density at temperature beta. So what I wanted to illustrate with this is sort of the fact that the von Neumann entropy includes two types. In quantum field theory, it includes, there are sort of two important contributions. There's vacuum entanglement, which dominates at short distances, and there's the actual like entanglement or the entropy of the stuff that's there. Like you have a bunch of particles flying around and they contribute to the entropy. So, and that's true in general. So let's see, the takeaway is that in the thermal state, the extensive volume scaling part of S of rho A is equal to the thermodynamic entropy.
Shouldn't the whole thing be the thermodynamic entropy?
S of rho A? No, this is a fine-grained entropy.
But you said that for thermal states, the von Neumann entropy was equal to the thermodynamic entropy, and this is a thermal state.
So that would be true if you talked about the whole system. So when I say it's thermodynamic entropy,
Okay.
so if we talk about the whole system, then in a thermal state, S of rho would be equal to S thermal of beta.
If you let L go to infinity.
Right. But now what we've done is we've started the thermal state, we've reduced to a subregion. But the point here is that even locally, the extensive piece is the thermodynamic entropy. Okay, and this is supposed to give you some intuition for how to think about entanglement entropy in quantum field theory. Okay, so quantum field theory is tricky, but it's just a bunch of stuff flying around, and if you have a region A in quantum field theory, there's kind of two types of stuff that you have to worry about. There's the virtual stuff that mostly is at short distances. And that's some short distance entanglement. Does it contribute to the entanglement entropy? Yes, if it's near the edge, okay? If you have stuff if you have some short distance entanglement that's not near the edge, that does not contribute to the fine-grained entropy because taken together, these two particles are pure. Okay, so the virtual stuff contributes if it's near the edge. And then you have some actual like physical particles. I'll make those bigger. I don't know if they're bigger. Okay, then you have some actual physical particles like the gas in this room that's flying around, and whether that contributes depends on what it's entangled with. If it's just quantum stuff in a pure state, then of course it does not contribute to this fine-grained entropy. But if it's entangled with the rest of the air in the room, then it'll contribute to the von Neumann entropy, and the amount it'll contribute if you're in something like a thermodynamic state, something like a thermal state, is going to be the thermodynamic entropy. I should add the caveat that I draw entanglement. I often draw entanglement as these little wiggles connecting things, but entanglement is not a two-party thing. Okay, entanglement. You can ask how much is this particle entangled with everything else, but except in very special situations, it's not just entangled with one other thing. It's sort of entangled with the rest. And and I'm just drawing it that way to be able to draw a picture. Okay, questions? Yeah.
If I have a universal constant, how should I visualize it?
If you have what?
If I have a universal constant term, how should I visualize it?
You mean how do we make sense of the universal constant term?
If, for example, in a topological theory. But
Yeah. I have no idea, and it really bothers me. Okay, there are terms like so the so in 4 dimensions, the coefficient of this term is called A, and it's a very important thing. Maybe that's why it's called A. In the thing Ikun is talking about is in odd dimensions. There's a finite term, which is called F, and it's also very important and universal. And these constants also show up in other places in quantum field theory. That's why they're important. But at least I don't feel like there's a good. I don't feel like from thinking about the entanglement, I don't have any sense of why like some term way down here would be something important. It's weird. It's weird. You can do a bit better in some special situations, but it doesn't have. I don't know how to see. I don't know how to think about it intuitively.
I have a question.
Yeah.
So you wrote that if L is much greater than beta, then on the bottom right, on the right board,
Okay.
if L is much greater than beta, then the entanglement, the von Neumann entropy of region A goes to that thing, which is the volume of A times the thermal entropy at temperature beta. But if L is going to infinity, then the density matrix should just go to like the full thermal density matrix. In which case, the von Neumann entropy should just be the thermal entropy.
Yeah. This is the entropy density.
Oh,
Is
I
that what's
see.
bothering you?
Okay,
Yeah. That's thermal's entropy density.
got it.
While I think of it, let me tell you that there's no lecture next Thursday. Okay. So don't forget. Okay, the next topic that we are going to be discussing is quantum information in Hawking radiation, black hole evaporation. What I want to do is to sharpen the information paradox that we talked about briefly before. Let me remind you what the paradox was. The Penrose diagram for an evaporating black hole looks like this. Okay, so the spatial slices at early times have they have an outside. Remember, this is infinity here. This is future null infinity. So we live here. This is the event horizon, and the inside of the black hole is this triangle. The singularity is this. Okay, so at early times, a spatial slice looks like that. And we're assuming that this black hole formed in pure state, like a pure collapsing star. This is a pure state. But now there's Hawking radiation. The black hole shrinks. the Hawking radiation here is entangled with its partner Hawking radiation inside the black hole. And if we look at a spatial slice at late times, it looks like this. And the quantum state on that late time slice is approximately thermal and therefore mixed. That's the problem. And the way we're going to think about it is in terms of the entropy of the radiation. Okay, so to think about the entropy of the radiation, what I want to do is pick a region out here that I'll call R. So that region is, R is for radiation. Okay, so we're collecting, that region contains a bunch of the Hawking radiation. Depending on where I put this, depending on exactly where I put the endpoint here, it may contain hardly any Hawking radiation, or a lot of Hawking radiation, or all the Hawking radiation. So if you like, you could think of putting sort of an imaginary line here. So there's a T here that labels the endpoint of our region R. And if you are like if you have a bunch of like Hawking radiation collectors far away from the black hole, then you're collecting the radiation in region R that's coming out from the black hole. Okay. So the question that we want to ask and the way we want to phrase the paradox is by asking the question, what is the fine-grained von Neumann entropy of region R as a function of T? I don't really have to write as a function of T there. I could just tell you where region R is, but it can be, let's think of the endpoint of region R as being a function of T that we can extend forward in time. Okay, is that setup clear? We're going to be talking about this for the rest. Okay, so this should be clear.
And then we're going to like take the limit that R is like the whole space or something and see if it's pure.
We can, well, we don't actually have to take it to be the whole space. We just have to, in fact, we can take R to be something that starts like 100 miles from the black hole, and then we just look at that as a function of T. Now, if it's not all of space, we don't expect it to be pure, but we can still ask what is its fine-grained entropy, and in fact, even looking at that region far away will be enough to see a problem. Okay, it's clear? Questions? Okay. And what we're going to discuss today is roughly what we think that should look like. And in contrast, what Hawking's calculation suggests that it looks like. They're not the same. And we're going to do this using, at first, we're going to use a very rough Qbit model for how we think Hawking radiation should work if it's a unitary process. So the Qbit model is the following. Imagine that the black hole is a bunch of qubits. Okay, so just a bunch of qubits. There's NB of them. And that's in some quantum state of the NB qubits. And then you have the radiation, which is also a bunch of qubits. And there's NR qubits in the radiation. Okay, we are not keeping track of like the vacuum entanglement and all that kind of stuff right now. This is just a rough toy model. In fact, it's a very good toy model. It's surprisingly good. But it's a rough toy model for how this is supposed to work. You should think of the radiation as being you should think of these qubits as being the Hawking modes that have been emitted. The black hole part, you should think of as being some microscopic quantum states that underlie the black hole. They're not like quantum fields inside the black hole. It's not that. It's some quantum gravity junk that we don't really know how to explain or describe. And then the dynamics are that at each time step, the black hole evolves by some complicated unknown physics, which we could think of as a random unitary. And emits a qubit with probability gamma, which you should think of as the rate for Hawking radiation. Okay, so that is, there's a lot of there's random evolution going on in the black hole, which models some complicated quantum gravity physics that we don't understand. And then every once in a while, one of these qubits gets pulled off and moved into the radiation. That's the model. Obviously, in modeling it this way, we're assuming that black hole evaporation is unitary. Okay, this is just an assumption. And that's how we're going to approach this. We're basically going to assume that black holes are unitary and obey quantum mechanics, and see what it tells us and where it leads us into trouble. And then our goal, of course, is to find S of the radiation as a function of t. And we could do this in, well, the claim is that it looks like this. So here's t. It goes up for a while. So why is it going up? It's going up because initially there's no stuff in the radiation. Okay, so it starts at 0. The radiation consists of no qubits. So it starts at 0. And then what you're doing is you have this very entangled system in the black hole, and you're peeling off a few qubits from that very entangled system. So those are just going to be in a maximally mixed state. And therefore, it's going up just as log 2 times the number of qubits you've peeled off. But eventually, it turns over and goes back down to 0. Okay, the fact that it goes back to 0, that's easy to understand. When the black holes, eventually all of the qubits go from the black hole into the radiation. So this is when the black hole is gone. When the black hole is gone, well, we're doing unitary evolution. So when the black hole is gone, the radiation is pure, and therefore has to have 0 fine-grained entropy. The surprise here is the fact that there's a sharp transition. Well, it's a little surprising. It's surprising to me, anyway. There's really a sharp transition from it growing to it decreasing, and we're going to see that from this model. Okay, so I'm going to state a precise theorem for this model. But first I need a definition or two. Okay, so the trace norm it'll denote M1 is the trace of the square root of M dagger M.
Sorry, question.
Yeah.
Is it immediately obvious that the first statement is consistent with the second one? In some sense, when it emits a qubit, there's some information that's being lost.
By emit, I really just mean nothing's happening to the full quantum state when I say that we emit it. I'm just saying that we now consider it to be part of region R.
But the unitary evolution is just the black hole, it's not black hole plus radiation.
Right.
So the black hole has lost something. So the whole thing I can understand, black hole plus radiation is good.
Well, the unitary acts on the black hole, and then we emit a particle, and then the unitary acts some more on the black hole, and then we emit a particle, and then it acts some more. So there's nothing non-unitary going on.
So the black hole is losing something, right?
Yeah. Yeah. The emission process is not unitary for the black hole, but it's clearly unitary from the point of view of the full system, right? Because nothing's happening to the full system. We're just redefining the edge of the radiation region.
Right. What's confusing is just the black hole by itself still evolves as unitary. Like if it were a full system, I'd understand that.
Well, it only evolves unitarily when it's not emitting something. So it's evolving unitarily and then it's emitting something. That's not unitary for the black hole. And then, okay, does that make sense?
Yeah.
The 2 norm, M2, is the square root of trace M dagger. It's called the L2 norm. And we can use these to measure distance between density matrices. So the distance is like rho minus sigma. So that's why I'm introducing these, because the result that I want to state is basically I want to say that, well, let me say where we're going with this. When you have a small enough piece of the system, the density matrix will be maximally mixed. And I want to quantify that fact. I want to quantify that statement. So to quantify that, we need to be able to measure how far density matrices are from each other. So that's why we're doing this. So that it's straightforward to show that M2 is bounded above by M1, which is bounded above by root n, that being the dimension of the Hilbert space, times M2. Now we're going to consider random states. So a random state, I'll write as psi of u, which is a unitary operator u acting on some reference state. The reference state is going to drop out. It's not going to matter. Just pick your favorite reference state and act on it with a unitary. This defines psi of u. And when we talk about random states, we're going to choose a random unitary. So Don Page proved the following theorem, which is the origin of that spiky curve, which is called the Page curve. So Page theorem states that the integral over unitary matrices of this trace norm rho A for rho A of u minus 1 over size of A, 1A. So this is what we want to calculate. Let me say in words what this is. This is the distance of, so we have a subregion, we're picking a subregion A. Well, let me say our full Hilbert space is HA times HB. Okay, and then we're picking a subregion A from a random unitary state and asking how far is that from being maximally mixed. The integral du is the integral over unitary matrices with the Haar measure. Haar measure just means the measure on unitaries that respects the symmetry. I'm not going to talk about doing unitary integrals. They're fun, but it would kind of lead us afield, so I'm just going to state the theorem. So the theorem says that this is bounded above by the square root of size of A squared minus 1 over the size of A, size of B plus 1, which you can, a little more intuitive way of writing it, but a slightly weaker statement is that it's bounded above by A over, by the square root of the size of A over the size of B. And this is for A and B, both much bigger than 1. So I'm not going to talk about the proof. The proof is in the lecture notes of Harlow, which I'll post a link to on the webpage. We can restate this in terms of the entropy. And where the point of this is going to be that this is an incredibly strong bound. So I'll be able to quantify this when we talk about the entropy. So in terms of the entropy, this says that the integral, the average over unitaries of the entropy of rho A of u is equal to the log of the dimension of A minus a half dimension of A over dimension of B plus subleading terms. For example, say region A is 1,000 qubits. Region B is 1,003 qubits. And AB, the full system, is in a random state. Then we'd expect to find the entanglement entropy SA to be about 1,000 log 2 minus 2 to the minus 4 plus dot dot dot. All these, like dimension of A, dimension of B, these are all exponentially large. These are the size of the Hilbert space. So what this is saying is that you take a system, you cut it almost in half, then the smaller half is going to be maximally mixed to extremely good approximation. That's this term. So the corrections to it being maximally mixed are exponentially suppressed in the number of extra qubits in the other half.
Here, if we've done that integral, what would you do?
Here?
So when you write this expression, is that integral being done?
Yeah, this integral can be approximated, and this is the answer. I didn't do it here. Yeah. Okay, so that's the origin of this spiky curve. So let me write it again. So now I can write a formula. So the qubit page curve as a function of the number of qubits in part A. Let's put the number of total qubits here. Then S of A is, it's a very good approximation, min of the log dimension of A, the log the dimension of B. So if we plot that, it just turns over in the middle. And looks like that. This isn't quite the curve as a function of time. This is the curve as a function of how many particles have been emitted into the radiation. But if you can easily go from one to the other because we just have to know what the rate is as a function of time. And you can, so for a black hole, it's slightly more complicated by the fact that the rate depends on the temperature depends on the mass of the black hole. Okay, so black holes have a time-dependent temperature and a time-dependent rate for emission, but it's easy enough to go back and put in that time dependence, and that gives you a version of this curve which looks basically the same. It just, depending on what black hole you're talking about, the curves are not exactly linear, and the transition point is not exactly in the middle, but it looks basically the same. The curve goes up, and then it suddenly turns over and goes back down. Yeah.
So how reliable is the curve near the transition point? I thought all this was in the approximation that I think A and B are sufficiently large.
Yes. So the corrections to the entropy were here.
Yeah.
And so when A, well, when A and B are the same size, up to terms that are much smaller than A and B, the corrections become sort of important. And what we expect to have, so on this plot, that correction is, okay, so if we take n total to infinity, then you won't see it on this plot, that correction. But at any finite n total, like say there's 1,000 total bits here, this will get slightly smoothed out and it'll actually look like that. It is important though, because it's the leading correction in large N expansion. So the corrections in a large N expansion are very small, but there's very small everywhere, but they're slightly bigger right at the tip and serve to smooth out that curve at finite order in large N. Other questions? So now we can apply this to the black hole and talk about the page curve for the Hawking radiation. Okay, so now I'm plotting this as a function of t. I'm going to plot three things. Okay, so first I want to plot the prediction of Hawking's calculation, which we did earlier. Okay, so when we talked about Hawking radiation, we said the Hawking radiation was in a mixed state. It was thermal, and we want to plot the von Neumann entropy of so S of rho r according to Hawking. That's going to have two contributions. It's going to have this short distance entanglement virtual contribution, which is infinity times the boundary of region R. And it's going to have a thermodynamic contribution, just like when we discussed the thermodynamic, just like when we discussed this log cinch in two-dimensional CFT at finite temperature. There's a contribution of UV stuff at the edge of the region. And then there's an extensive contribution, which is the thermodynamic entropy of the stuff in the region. So what I'm going to plot is I'm going to subtract off the UV divergence by just subtracting off the value of the von Neumann entropy at time 0 for this region R. So it starts at 0, and it's, to very good approximation, it's just going to be the thermodynamic entropy of the Hawking radiation itself, which is in a thermal state. It's straightforward to calculate the entropy. It's a little bit, well, it's not that straightforward in more than one dimension, because the black hole is evaporating, its temperature is changing, so you have to find it as a function of temperature. But it's going to give you some curve, looks like that. For two-dimensional black holes, actually it's just perfectly linear. Then at some point the black hole is done evaporating, and it's just flat. Okay. So that's a plot of this quantity here. S of rho sub r according to Hawking, subtracting off the time 0 contribution. Does that make sense? See if I have another color that works. So the next thing I'm going to plot is area over 4 of the black hole. So remember, in black hole thermodynamics, black holes seem to have entropy area over 4. So the black hole is evaporating, so the area is shrinking. And actually, the further it goes, the area is shrinking faster. This is r squared. So something like that. So if black hole evaporation is unitary and sufficiently complicated that we can use Page's Qbit model, then what we expect for the actual von Neumann entropy is that it's going to start out thermal, but eventually, for the same reason that the Page curve of the Qbit model turned over, it's going to turn over. So it's just going to follow the minimum of these two curves. So this is the expected unitary Page curve for S rho r minus S rho r t equals 0. So if we knew how to calculate the fine-grained entropy in a full theory of quantum gravity, and if black hole evaporation is unitary, then that's the curve that we expect to get. And if area over 4 is really the entropy of a black hole. Yeah.
Why is there no subtracting p equals 0 analog for the area over 4? I don't know.
Because let's see. What I'm trying to mimic is something like the Qbit model. So in the Qbit model, there was a black hole, there was a bunch of qubits, and there was the radiation, which was a bunch of qubits that accounted for the Hawking radiation. The problem and the reason that we have to subtract off something in these two cases is that so region R now is this region here, right, in the Penrose diagram. And the problem is that this has a bunch of virtual contributions from short distance stuff near the edge that were not in our Qbit model. Okay, so it's like the more realistic model has the Hawking, the more realistic model has the black hole, the Hawking radiation, and a bunch of entanglement between the radiation and some additional system, call it aux, which is like this region here, aux. That would be a more like realistic picture of what the entanglement actually looks like around the black hole. And that contribution is infinite but constant in time. So what we're doing in this picture is we're just trying to get rid of that annoying extra piece. And what's basically happening is the Hawking radiation that comes out has to be entangled with the black hole, but the black hole only has so much in it. It only has so many states available to it, and you just can't create an arbitrarily large amount of entanglement by entangling with a finite system. the most entanglement you can get by entangling yourself with a finite system is the log of the dimension of the Hilbert space of that system. And in this case, the maximum is set by the entropy of the black hole. It's not really that the Hilbert space of the black hole is finite. That wouldn't be the right way to say it, because the black hole can get bigger and bigger, and so then it really has sort of an infinite Hilbert space. But at a given temperature, there's only so many states available. It's the usual situation in thermodynamics. At a given temperature, there's only so many states available. Those states are counted by thermodynamic entropy of the black hole, which is area over 4. So the most entropy you can get by entangling yourself with the black hole is area over 4. And this means, in particular, that the information paradox is not just a problem when the black hole is gone. Okay, I think the way I probably said it before, and maybe the safest way to state the paradox, is that when the black hole is gone, you have a mixed state, so you're in trouble. Okay, so that's like talking about this part of the picture. When the black hole is gone, you have a mixed state, so you're in trouble. But actually, you're in trouble way earlier. You're in trouble already when the black hole is approximately half gone. This isn't quite half, but it's an order 1 fraction of the black hole. So if the entropy even looks like this or something, you'd have a problem. So the problem occurs much earlier than the evaporation of the black hole. And that's one of the reasons that it's hard to solve the problem with, like, for example, some physics that just enters at the Planck scale. A popular solution early on in the information paradox was to say, well, we don't really know what's happening when the black hole is Planck-sized. Maybe it like shoots out a bunch of information at the last moment because of some Planck scale effect. But that's really not gonna do it. You have a big problem way before the black hole gets near the Planck scale. Questions? Yeah.
So the final entropy of the radiation, is it always expected to be greater than the initial area over 4 of the black hole?
Let's see. I don't know about always. You mean in Hawking's calculation?
Yeah.
Yeah. It's typically higher, just because it's not adiabatic. The thermal entropy of the radiation is bigger than the entropy of the black hole that it came from. Anything else? Okay.